Hey everyone, and welcome. Today, we're going to take a deep dive into the heart of how our programs actually work. We're going to explore how a powerhouse language like C++ handles one of its most critical and sometimes trickiest resources, memory. I mean, think about it for a second. Your photo gallery app has no idea if you're going to add one new picture today or 100. So how in the world does it prepare for that? Well, the answer is this really powerful concept called dynamic memory.
So it really boils down to two main flavors of memory management. You've got static allocation, which is kind of like booking a dinner table for exactly 4 people weeks in advance. It's fixed, it's decided before the program even runs. But then you have dynamic allocation. That's like renting out a whole event space. You can add or remove tables on the fly as the party is actually happening. Total flexibility.
Now, where does all this happen? Well, the computer's memory is basically split into two main neighborhoods. You've got the stack, which is for that fixed dinner table. It's super fast, super organized, and the computer cleans it up for you automatically. But our flexible event space, that's the heap. It's this big, open pool of memory we can grab from whenever we need it. The only catch is, we're responsible for the setup and the cleanup.
So if we're setting up all these tables in our big event space, how do we keep track of where everything is? We use a special tool called a pointer. Now, a pointer doesn't hold the data itself. It just holds the memory address of where that data is living. You can literally think of it as an address book for your program.
All right, let's get our hands dirty and see this thing in action. We'll start simple. Here, we've got a basic array of characters. Its size is fixed, right? So the computer puts it on that nice, simple, automatically managed stack.
Okay, now we create a pointer, we'll call it PTR, and we tell it to point to our array. In C++, the name of an array pretty much acts as a pointer to its very first element. So just like that, our PTR is holding the address of that first letter, H.
And boom, this is where you see the real power. We can use that pointer, that address, to go directly in the memory and start messing with the data. Just by using PTR, we've changed the third letter in our original string. Pretty cool, right?
So, how do we use this awesome power on the heap? Well, there's a 4-step life cycle, a set of rules that you absolutely have to follow every single time. First, you declare your pointer, your address book. Then you use new to ask for some memory. You use that memory, and then, and this is the crucial part, you have to use delete to give it back.
Step 2 is all about that new operator. Think of it like you're filling out a request form. You're basically telling the operating system, hey, I need a chunk of space over on the heap, just big enough to hold one integer. If the system says yes, it carves out that space and hands you back the address, which you store in your pointer.
And this brings us to the other half of the deal. This isn't a suggestion, it's a contract. When you're done with that memory, you must explicitly release it with the delete operator. This tells the system, hey, I'm done with this spot. You can have it back, so it can be used by something else.
So a request with new, a cleanup with delete. Sounds pretty straightforward, doesn't it? It's a powerful system for sure, but with great power comes, well, you know the rest. And here, it means there are some serious ways this can all go horribly wrong.
First up, the big one, the memory leak. This is nasty. It's what happens when you grab some memory from the heap using new, but then you somehow lose the pointer, the address to that memory. Now that memory is completely orphaned. It's still being used, but your program has no way to find it, no way to use it, and most importantly, no way to ever give it back.
Okay, let's walk through a classic example. Check this out. We've got 2 pointers. PTR1 is pointing to a little block of memory that holds an 8, and PTR2 is pointing to a totally separate block of memory that holds a 5. So far, so good. Everything's accounted for. But now, watch what happens when we run this one line of code. PTR2 equals PTR1. All we're doing is copying the address from PTR1 over into PTR2. Now they both point to the 8. But what about the memory holding the 5? We just overwrote the only address we had for it. It's gone, vanished. That memory block is now floating out there totally inaccessible. And that is a memory leak.
All right, so if memory leaks are about losing track of memory you should know about, the second big danger is kind of the evil twin of that problem. It's called a dangling pointer. This is a pointer that's still holding on to an address for a piece of memory that's already been freed and given back to the system.
So for this scenario, picture this. We have 2 different pointers, PTR1 and PTR2, but they're both pointing to the exact same chunk of memory on the heap, a spot that's holding the number 8. This happens all the time in real programs.
Now we do the responsible thing we call delete PTR1.
The memory holding that 8 is now officially free. Awesome. But, look at PTR2. Nobody told it that the memory is pointing to just got wiped. It's still holding the old address. It's now dangling, pointing to garbage. And if you try to use PTR2 now, you could get nonsense data, or more likely, just crash your entire program.
Okay, so managing new and delete by hand is, let's be honest, a complete minefield. One tiny mistake and everything can come crashing down. There has to be a better way to get all this power without so much risk, right? Well, of course there is. We just need to build a smarter system using the power of object-oriented programming.
The solution is to build what we call a smart container. We create a class that basically acts as a protective shell, wrapping up that raw, dangerous pointer. And the real magic happens in two special functions. The class's constructor automatically calls new for us when an object is created. And even better, the destructor automatically calls delete when the object is destroyed. Just like that, the manual work is gone, and the risk of leaks and dangling pointers, it's basically eliminated.
This is fantastic. We've built a safe, automated system. Problem solved, right? Well, almost. There's one last catch. Our new awesome DynArray class only knows how to handle integers. So what happens when we need a dynamic array of doubles or characters? Are we seriously supposed to copy and paste this entire class for every single data type we might need? No way!
And this brings us to the final and most elegant solution, a C++ feature called templates. Just look at the difference here. On the left, our code is hard-coded to use int. But on the right, we add one little line at the top, template class T, and then we replace every single int with this generic placeholder, T.
And the result is just so powerful. We write the code for our safe container once, and then anytime we need a dynamic array, we just tell the template what kind of data we want to put in it. Need an array of integers? Dynar int. Doubles? Dynar double. We finally created code that is safe, flexible, and completely reusable. So let's just step back and look at the journey we just took. We started with a very real problem, data that doesn't have a fixed size. We found a powerful but dangerous tool to solve it, dynamic memory and pointers. We came face to face with the twin dangers of memory leaks and dangling pointers. And finally, we engineered a truly robust solution using classes and templates to hide all that danger away, giving us all the power without any of the chaos.
You see, this whole process of taking something complex and dangerous and hiding it inside a safe, simple interface, that's a core idea in programming called abstraction. It is the secret to building incredibly complex software without going completely insane. So the real question to leave you with is this: where else can we apply this powerful idea to tame complexity and build better, safer code?